let's save as. Now we're going to start with the Whitewater. Let's call this surface Whitewater sim. The reason why I mean surface is because we're going to have like splashes and mist and other things in a different setup. So for now, what we want is the regular Whitewater that just covering the surface. Okay, let me create another one of this. FG as foreground, Whitewater theme. Color this like that and dive inside. Object merge. I want to bring the compress, so from the fluid, out compress. The compress is this, right? So I'm going to hide everything, and from that I'm going to actually separate. I'm going to blast out the surface and the velocity. So let me do that. It's the same thing that we did. I'm going to blast surface and val. Oh, sorry, and val. So here we can say this is out volumes. And if I want to just have, I don't know, just maybe I just want to have the surface here as well. Surface. Yeah, the surface. Yeah, and then we can use the Whitewater fourth. The liquid come into here, and let's define what we want to emit from. So the first step is what velocity do we want? And in this case, we can leave as default for now. And we don't need any emission from the curvature, so I'm going to disable that. I also don't want any emission from acceleration, and I do want from vorticity, but I want to get more, like from 12 to 30. And then we can visualize that. It might be hard to visualize like that. You can see it a little bit, so I'm going to make the background dark. Oh, sorry, dark, and you can better see it. Now there is one thing that the volume, we need to increase the volume here to get a little bit more definition on the interpretation of that. So it's good. What that gives us is just the emit volume, that from that emission that's going to get like the Whitewater that we need. And I think that's good. We can do like a file cache. I'm going to call this Whitewater force foreground surface. Okay, this is the fourth. And let's plug this in here. Out emit. Great. Now we can do like a adopt network. Let's call this FG surface Whitewater sim. start from the frame 1. It's good. The Whitewater is the part that is hardest on your system resources. So if you don't have a lot of RAM, like memory, like if you have like a 32 or even 64, depending on the amount of Whitewater that you want, you might need to split that. The good thing is that Whitewater blends really nice when you merge them together. So what I'm going to show you is how you can split your simulation into multiple steps and merge them afterwards. So for that, what you're going to do is you're going to get like the emission here. So for example, I can do like the emit from this, and we can have like a different range for that. So for example, I can do emission from 2 to 3, and then another one from 3 to 5, for example. You know, they both will work. They're different emissions. One is grabbing the slowest particles, and the other one is grabbing the highest, more the particles that are flying a little bit faster. You know, so this is one way that you can approach that, and you can even like go even further with that and come to the vorticity and get like less vorticity ranges. Like this one goes from 12 to 18, and this one goes from, I don't know, like 18 to 35, just less in general, you know, like, and you can combine them, or you can keep that as is with one source. Let me just go back to 30, and let me go back to 4, and you can create 2 different simulations. Let's do one here, and then I copy and paste that. Okay. Whitewater object, Whitewater solver. You don't need to add gravity in this one because the solver already has into the forces the gravity attribute and also the buoyancy that makes the particles that are under the surface to go to the surface. And so you don't need to touch on that for now. All right. So let me start doing one thing. Add state attributes. That's really key because the state attributes means, let me draw it for you. Okay. If here is the surface of the fluid. Okay, this is the surface. Particles there are on the surface, like Whitewater there on the surface, they are called foam. Particles there under the water, under the surface, they are called as bubbles. And flying particles are spray. What it means is like based on the position of the particles, it's going to give an attribute from 0 to 1 to define whether these particles belongs to the spray group, to the foam group, and to the bubble. From 0 to 1 means that sometimes the particle is almost leaving, is halfway through, and then it can have like a little bit of foam and a little bit of spray attributes into them, or vice versa, or with the bubbles as well. So that's what the state attribute give us, is just give these attributes. That's very useful. I want you, the Whitewater scale, you can go like with the same resolution of your fluid. I'm going to go a little bit lower than that, but I have a lot of RAM, so it's okay for me. Try out if you do the double splitting option, like you can keep that like a larger value here, because scale is very definitive in the amount of particles that you're going to have from the simulation. What I mean is that it doesn't allow to have a lot of overlapping particles below this range. So if one particle is here and another one is 0.04 away, it allows to create another one, but it doesn't allow to create a lot of particles on top of each other. And this is the radius around each particle that's going to define how much particles you have in your simulation. So this should be at least double of that, so 0.8, and we can leave that like that. The emission amount is a multiplier on the emission, so you can start with something small and see how much particles you have, if your system handles it, and then you can increase from that. The lifespan, we can reduce that, so after 3 seconds, particles are going to die with some reasonable variation. And then here also the seed is key, you know, like you can set like a seed here, because when we copy, we're going to change the seed. And I'm going to get like 50 in this one and add a little bit of noise. I'm going to have like a frequency of 4. And the amplitude, small amplitude is enough normally, because this is a bit aggressive, this noise. Limits, we're going to copy the limits from our simulation, right? So we can just come in here. I'm going to set to manual and can come here and grab this, copy parameter. And here we can just change this, is 5, it's fine. So I copy the size. Limit size base relative reference, so it's the same. And the limit here is 4.96, something like that. It's good. So we have that, and we don't need anything else here. On the forces, okay, so the base advection strength is how much the ocean velocities from the flip simulations that we have are going to advect into the velocities of the whitewater. So I want to have like a strong advection, so I'm going to increase this to 8. And also this, it means like the buoyancy by depth. It means like the water, let me draw this too, because this is key to understand what's going on. So if you have a water flying here, right, like this is a drop of water, this is the ocean, okay, we have a flying water here, you have like the waves, and it's all flying. And so the advection strength means that if a whitewater particle that I'm going to draw as pink, it's inside this, it's going to advect strongly with the same velocities of the ocean. But because we're cutting this out in this area, this is bubbles and this is spray. Is the depth, is how far inside it is. So if it's just outside the whitewater, that's in this range, is spray. If it's on the surface, doesn't mean to be the surface of the water here. From every surface, even if the flying like water in here is also in the surface, and inside is bubbles. So what this means is that if the particle is inside or in the surface, it's going to strongly advect with the same velocities, is going to keep with the same velocity of the ocean. If the particles start to fly, it's going to keep flying with its own speed. It's not going to be affected by the ocean at all. That's what we need, because once it's outside the ocean, rules of physics is going to be applied to them. Forces, velocities, and gravity and all that. And it's not the velocity of that particle. So that's it. All right. So moving forward, let's go to the phone tab. And here in the phone tab, we're going to have like a few attributes. The density control is how far inside and outside the range is going to affect. And the stiffness, it means how much the shape of the particles, they clump together and they stay clumped and with more graphical shapes to it, or how much they just spread apart as a spray without even any shape, just like random particles flying over. Um, I like to increase it a little bit, like to 3, so we have a little bit more, and a variable stiffness. What it means is, again, this is based on depth. Every time you see depth, and the ramp means like from bubbles to spray, from inside the surface field to outside the surface field. And in here is the same thing. The stiffness, once the particles are under the water, they don't have like the stiffness. And once they are sprayed, they also don't have, they fly like with little particles. That is very normal to have like this behavior. The erosion means when particles are very clumped together, they live longer. Once they spread apart on the surface and stay like just floating solo, they're going to die sooner. So we can enable that. We can reduce the strength of that, so it's not going to erode that fast, and we can keep the preservation height a little bit longer. It just reducing the general effect of the erosion and keeping the particles on the surface longer. So salt water helps to maintain salt foam longer. If you work in a river, something with not salty water, normally the foam dies faster, so they erode faster. Also, the repellents allows you have like that shapes, the cell shapes that we see when the white water is on the surface. They created these cell shapes like like this. Oh, let me go here. Yeah. So they have like they start to have more like this pattern of like cell shape. The particles that are here, they got attracted to the center, and they clump in these areas, and give like some holes, so they repel each other until they clump together, because this is going to repel in this direction and this in this. So the particles that are repelled from these are going to be repelled from this. They're going to more or less clump in the center of this. So let me set some parameters here. The size is in meters, so like 10 centimeters is the size of these holes that you're going to see in the surface white water after some time. 6, I think it's good. The other one was too large. And the strength, I'm going to reduce that a little bit. Like, yeah, noise range, I want to have like some noise at least in everything, just to break up, not to get like really round shapes. And yeah, and that's it. The adhesion is that like enable depth control and upper surface only. It means we're talking about the surface of the water, the white water that's on the surface and above. And the depth control means that if the particle, the white water, is up to 0.6 away from the surface, is going to be all the settings that we did are going to apply. And if the velocities of the particles that are flying away, if it's like the offset, the velocity angle is less than this number from the velocity of the fluid surface, it's also going to allow the particle to just fly. If it's more than that, the particle can just fly freely and not going to be affected by all that. And if it's away from the surface, it's also not going to be affected of any of that. It's just going to fly in the natural trajectory based on the forces of that we set, like the gravity and all that. Yeah, that's it. We keep working on our next class. See you there. Also, like the pop drag that I want to enable, you can look extra sources, particle forces. So here it is. And I want to have like the pop drag to have like the same one, 0.1. It's good amount, just a little bit of air resistance to it. And also I want to create a group, pop group. Same thing that we did, but now it's not droplet. We want to affect the spray. So I want to name this spray, and I want to Yeah, we can preserve the group. It just means like it's going to every frame is going to keep updating it. Yeah. And in group is at spray is bigger than 0.2. Right. So if the spray attribute 0.2 is bigger than this, it's going to be affected. Or maybe 0.15. Yeah. It's good. So now it's adding to the group. The group name is spray. It's not the source group, sorry, is the group name that should be here. And then we're going to have like the pop wind that is going to be affected only this group. So I'm going to select that. I'm going to add group here, select, and we're going to give the same velocities that we had like there. Velocity of 6. I want to give a little bit of up velocity just to like sometimes get the lift for the storm, like just you can see it sometime. And here's the same thing, 1.5. The surf scale is 3.5. And yeah, we can keep like that. So this is good. It's all set. We need to set the volume source and the emission. So you can just do like this. One level up, another. The first points is in this level. Then we go in one level above that, and we can have like the out volumes. And for here, we have out emits. Okay, so we have the emission, we have the volumes, and we have all set. Okay, if you want to do split your simulations for your computer to handle, you can do like that. You can split these apart, right? So this is 1 and 2. And for this one, you need to come in here and you need to change the seed, of course. And that's basically it. It's going to give you a nice volume. If you change, if you create another Whitewater source, you need to change the emission to do something to another emission. You create another emit and then you just replace that. That just allow you to keep building if you cannot get like very very strong parameters, like if it starts crashing. Another solution is to work on Linux. It allows, it's much better, it has a much better memory administration. So it just allow for you to have like maybe 30-40% less memory usage than in a Windows with the same resource, same computer, same hardware. So it's really good. I use normally Linux for simulating heavy stuff, and most of my simulations I use Linux. So yeah. In here, that's all. You can change a little bit the pop drag. You can have a little bit of variations if you want to build like just to play with different dynamics and variations for this system. I'm going to keep in one. I can handle one, so for me, I will keep in one, and I change my emission back to 1. I will get like this to 2, and this to 4. This is the setting that I'm going to use. It's going to give roughly 50 million points and going to require, I'd say, like at least 120 gigabytes of RAM to run with these settings. If you have 32, you can split in smaller chunks and combine them later. It works pretty well. So that's it, guys. I think. Okay. Before we leave, I want to do a couple of things. I want to do the same tricks. Like let's do a dop import dop.io, and I want to get like this one, and here we do. It's called Whitewater object, and the presets choose particles. We're just going to import the particles, but we're also going to save some space with attributes delete. I want to delete, I think I want to delete almost, maybe, yeah, let's do like that. Let me go back to 1, disable that, and then we go back to here, and I'm going to move 1 forward. So now I have the attributes that I want to keep. So I want to keep velocity, I want to keep age, I want to keep bubble, depth, poem, ID, life, almost everything, scale, and spray. Okay, I want to keep all that, and also a group delete. I want to delete all, and because we need to run that and that, if you have more simulations, you can set, you don't need to wait for that and then run this one. Let me set something here. I have a different viewport section where I divided this into 2. So I'm going to dive inside this one. And here I'm going to create a top network. I'm going to color this red so I can see it, and dive inside. So what I'm going to do a rob fetch in here, and you can copy this name. Copy it in here. Then I'm going to say wait for all. It means that this is going to run first. It's going to wait all this to be finalized before I do another rob fetch that is going to run my simulation. Just naming the same so I can see. So for that to work, we need to drag this in here. So this is what we want to run. I want to run frame range, and you can set all frames in one batch if you want. It means like it's going to run one, then another one, then another one. It runs for simulations, you need that. For other things, you don't actually need, so I can leave it off. And then this one, I need to drag this one here, and frame range, all frames in one batch. Yeah, that's what we need. If for something it doesn't work, if crashes or anything, you start to redo it, it's not going to work because the cache mode is automatically. You need to say to write files, or you need to come here and change the version. So it's not going to, if you have one version saved and you rerun this as this, is not going to save on top. It's just going to read that, because this is automatically is reading or writing files. Okay, then you need to come in here and say, generate node. It's going to ask you to save. You save and continue. So it's generating all these frames, 240 and all that. And then if I press again and say cook node, it's going to cook this one and then this one. I already have this cached, so I don't need that. Don't forget to save the path here correctly to the one that we have. So it's $cache, right? So yeah, it's all good. And here the same. I need to save this to $cache. You see, I have like some already here. This is my source that I had cached before. I'm visualizing the points. For that, you just need to enable the visualization of points, but the point doesn't matter because this is just the caching. And this is my final cache. Oh, I need to cancel because it's doing that. I need to load from this. Okay, yeah, that's something crucial. Before you do this sequence, don't forget to come in here and load from disk. Check, because then it might go on disk, save everything, but then when it's loading, If it's not checked, it's recalculating again and again and again the sourcing files. So it's better to do that. If you have a different simulation and you want to run like that, what you do, you split this. And if it's the same source, the same emit, you keep like that. It's going to wait for all, going to run this one. And then, yeah, maybe, no, you need to, the best way is to do like that. Because then you need that to finish before you starting again. So it's going to run one sim, and then going to run your other sim. You need to relink to copy all that like this, right? And then place this one in here like that. And that's how you run a lot of different sims. If you need to split them in different chunks. Okay, this is my, let me go in here. Yeah, this is the final sim. It look a lot of Whitewater, so, but because I'm going to work with the p scale and make it really tiny and very defined, it's not going to look like that. You see, when you go closer, you see that there is a lot of spacing. This spacing is defined by that, like 0.02. If you have like a larger area, the spaces are going to be more spread apart. So it look like they're almost close together, but just because in the height they are away from each other. So that's it. Okay, great. And the next lesson, we're going to get the setup for the other simulations. First, now we're going to process this to get the correct p scale and the effective p scale for that, and then we're going to work on the sides and the back, keeping the same idea of optimizing a lot these ones to run much faster. Okay, see you guys, and it's been a great journey. Bye. Now that we have cache our Whitewater, we need to process that, and that should match exactly our flip. So we should just come to here and we can copy all that. So let me get that, even including this. The disk mask is not necessary, I guess. So it's just, yeah, just that. So I'm going to Control C and Control V in here. Let's see if it works. There's a lot of points, so look like it's working, I guess. So it should just double check. We can just, yeah, look how nice it is. Everything being distorted the same way. It's matching nicely. We have this going on. I'd say some areas look a little bit under. The reason for that is just because the point itself, they have a lot of resolution, and because it's just individual point. And here is the mesh, and the flat areas we have like less geometry. So not like that. I want to see this. So you see, like this has a less geometry, but in general everything is working. So what's next? We could define the p scale, but what we can do for the p scale is to get the same as we get when you do from the shelf tool, and there is a node for that. So let me just go about, take this. So this node comes with the default Whitewater. I just did a few tweaks here, but basically what we have here is a base to define the p scale and the density, In this case, is more is working on the density, but you can also copy that for the p scale. And it's doing is just creating a fade on the density based on the depth. So if it's more like a spray, it's going to have like that less density. It's more towards the bubble also, and by the age as well. So once the particle born and once they die, they fade away, right? Like so, we can do that and also adjust the p scale. Just float. Yeah. Let's first have a look from the camera perspective. I'm going to hide everything else and I'm going to visualize the disks to see the size of our current p scale. Yeah, you see like we have like really big spheres here. They're really big. So what I want to do, I want to do this first. So now we created the density attribute. Let me go to here. What you're seeing here, like some areas that are fading out, is just because we are just saying that the alpha is the same as the density. So these areas is where you have like the fading density. That's nice. You see this pattern that's related to the point deform. But again, as I'm using the point deform here, because I just was testing everything, but the correct way, we can just come and grab I just want to grab that same spectrum distort node that we did for the main flip. I'm going to dive inside, I'm going to cancel this again, and I'm going to copy this guy, the spectrum deform that we did. And I'm going to go inside and paste it in. The position you see won't change too much, but the quality of the deformation is much more accurate. All right, so let me just see this guy. You see there is no issue again, and it's much more precise. So you can use that instead. Otherwise, you need to subdivide this a lot. So in some cases, you can't afford to use, as I discussed. You can't afford the spectrum. That's why I also show the point deform, because if the underlying surface is not the spectrum deform geo, is something else, then you need to do this way, and then you will need to subdivide it more or have more resolution on that. So now we can see here. See, the position is the same. It's like it didn't change that much, but just a little bit. So there's a couple of things we can just come in here and say that we can get the p scale, like do like a point flop. Dynamic p scale. You can do like a bind. The bind is a way to bring attributes in, so we bring density. And now we can do is to bring an export the p scale. Yeah. We can fit range the density like 0.4 again, or 0. Yeah, just 0.4, and we multiply. So we take the p scale that we have, and in this area we're going to have like smaller p scale that's going to match the density attribute. So here, and then multiply, we're going to now have like a p scale like very small in these areas, and the same size in this area. Yeah, you see very tiny points and bigger in here. So it's working okay. But I don't need that because this is going to fade away. So what I want to do is just generally, I want to just reduce the P scale in general. So what we're going to do, adjust float. We want to adjust the P scale. That's already the default thing. And instead of add, we're going to multiply, and we're going to multiply by 0.35, like something like that. It's good. And then we can have our out, Whitewater, main, Whitewater, points. Okay, why I say points? Because we can render them as points or as volume. For doing them as volume, it's a bit more expensive and take longer time, but it gives like even more details and better result. For that, we need to do like a rasterize attributes. Let me see, volume rasterize attributes, and we're going to rasterize the density, and we want to reduce that quite a bit. So I'm going to do like 1.2, increase a little bit the particle scale, and we should have something here. Yeah, you can see a little bit there, but you can definitely have like a you can definitely see that when you render. You just need to increase the shader, and then what we need to do is like the default thing that the thing is that for that to have like specular on the volume, that's something that Karma does really well, and Mantra in general, Houdini. There is a way of calculating the normal of the volume, and with the normal of the volume, you can actually have a volume shader that emulates a white water, and that also contains a little bit of reflection on it. So, and for that, you need just to bring these two nodes that Houdini provides when you do the default white water. And for the first node, there is some magic here. And the second node is just like calculating the gradient of the density. And when you merge that back with the original value, these outputs allow us to have like reflection on the shader. What is really going on here, for me, is a little bit of magic. It's hard to understand how these nodes allow us to grab the actual normal from the volume. I don't think it's something really simple to understand, and so I just take it and and say thank you. Okay. In this case, we're probably going to render them as points. So this is just like another way. So this is surf fall. Okay, and points. That's all good. So for the next one, we do the same, simulating the white water for both the back and the sides and the back, and that's going to be it for the white water on the surface. I'm going to go in the next lesson really quick around showing how we're going to do that, because it's the same thing that we did with flash resolution. That's basically it. And then in the end also we're going to have like larger P scale, so they get really visible from the distance, and you won't notice that it's lacking particles because the P scale is big enough to just fill in the volumes, and that's it. Thank you. So let's do the white water for the side section. I'm going to do the same thing. we're just going to copy, paste. The beauty of proceduralism. So this is side L, left, Whitewater sim. And in here, instead of grabbing this from here, we're going to grab this guy. So we're bringing the fluid from this one. So now it's the next section here. Yes. And let's dive into the parameters. Let's see if we're going to change anything in here. I think we can keep all like that. Yeah, we can keep everything the same. I think it's okay. Yeah, if you want, you can increase that like a little bit, but I will keep like as is. And this is Whitewater force here. I have the name already for that. And this one same. This is side L, surface sim. Let's dive inside. Let's see if we change any of the parameters. Yeah, for sure we're going to change the scale here. I'm going to increase mine to 5. If you feel like you can go above this number, it will definitely work. Of course, you need to try and see what your machine can handle, but don't worry if you need to get this to a higher number. It works okay. The foam location, that means how much, a little bit of offset from the surface. Because it's far away in the background, I want to increase this a little bit, like 1 centimeter. So 0.01, it's going to be slightly above the surface, but 1 centimeter you won't be able to tell, but it's going to be better for showing the white water on top of the surface in the back. This is a relative path, so it is still the same. Just let's check if we have the volume. Yeah, volumes and the emit, because we just copy, this will work. We are using that like a relative path. If you change this to not relative path, for example, it's going to bring from, maybe now it's already correctly set for this one, but when you have like this without the dots, it means that it's grabbing from this exact location. But instead, if you do like that, it means that it's one level above this one and it's going to grab this. Doesn't matter where we are. Okay, it go one level above and search for this. Let's go. You can reduce the emission amount if you feel like for that, because it's in the back. It's fine. It will work. Bubbles, I'm going to make it like even higher. The aging rate means like it's a higher chance of the particles to die. So if the bubbles are everything under the water, from the back we don't care at all about bubbles, so I'm making like 100%, 100 number. I don't know if it's percentage, I don't think so. And I'm also going to change the seed in here, and the noise also we can keep like as is. Limits, we need to change the limit. This one we need to grab from our fluid initial here. We need to grab from here, so I'm going to do the same relative path. And this is 0, but this one we need to copy this guy, copy parameter, and paste here. Paste relative reference. Yeah, and this one we can keep the same. So now it's correctly set for us here. Forces we keep the same. I won't change anything. I don't think we should change much here because it's just continuation of that main sim, so it should look more or less the same. Particles should die more or less the same, so it's basically the same with LED resolution. We're going to increase the size of the particles. And yeah, everything is set. This one is already, when you copy everything, is already set to here. And now like this one, we need to just change the name again. So this one, to copy, the name that I have. And yeah, I think it's we can work on the post processing for that. We probably need to copy that transformation that we have, and all this we will change for the other one. Like, so we can, yeah, maybe we can do it now. So I'm going to grab it. So we're going to grab all that, right? So spec distort, yeah, this one. We're going to grab this also. So all this, we don't need the displacement mask. So C, and then I'm going to delete this chunk and paste this one. We don't need the normal for that. So great. So let's do the same for the top, and we can set everything at once. So I'm going to do this, and then this is the top center. Again, right, this guy, yeah, you can increase that if you feel like, but basically I'll keep the same in here, not change anything. And here, let me grab, oh, the one surface whitewater sim. Let's dive inside, and we need to go also here because we need to grab the reference for the limits. You see, the nice part of the proceduralism is that if I even wanted to do more simulations, patches here and there, and if you want to go even further on the distance, you can decrease the resolution and but just copy the same structure. So it works really seamless and without any of the okay, so limits, that's what I'm looking for. I'm going to have like this relative, and this one, I'm going to copy this, why not? Copy, paste relative reference. Great. And yeah, I think we can now go even a little bit more. I'm making double of that. Poem location, yeah, we can keep like that. And maybe the emission amount I'm going to reduce to 0.65. We don't need a lot in the back, it's fine. Let me play with the seed just to get something different. Everything's the same. We keep everything the same. And now what we have is a sequence of nodes that we can just cook one after another. Let me just copy these guys. Okay. Now we need to copy this from here. Wherever we did at the end here, we have the same thing for that. So this chunk. If you want to select like a line of nodes, you press A and you do that, and it's going to allow us to just align everything and organize everything. So I'm going to do this. We don't need this. We don't need this. And this. So now select this and this. Great. Um, particle scale. We can do some tweaking on that um, later, but we probably won't reduce any of the p scale for those. We keep them as is. I think it's fine. Hmm. Yeah, I think the same for the side one. I also think we don't need to reduce the p scale like we did for the foreground. They are going to have less p scale. We can definitely adjust that when we render, but for now I'm disabling it and having just that. Yeah, awesome. So now we can build our tops. We can do the same thing that we did here for all these nodes. So we can run like a two of them. So let's do in sequence. So it's rob fetch. Get this guy. Let's copy the name so we see what's going on. And you can say is a frame range. Yeah, all frames. Doesn't need to have all frames in one batch. You don't need that. So you can actually do that. And you can merge. So both of them go in here. So they're going to run both of them simultaneously because it's just the source. But this one, what we need to do is just to grab this guy from here and rob and place this one. Oh no, sorry, it's this one. Am I doing the source in here? Source, yeah, source and source. Yeah, that's key too. Otherwise, if it's simulation, you can't do what I'm doing here. So now we can do wait for all, and then you can have like maybe the left one first. Doesn't matter, but rob fetch. Okay, bring it in. Frame range, and don't forget that in this case is all frames in one batch. And then another wait for all. Disconnect. Oh, sorry, disconnect. Connect. Then is the another rob fetch, so we can copy this guy, plug in here, come to the rob, and yeah, this is the same. And let's just rename this. So what's going to happen is that it's going to run both of them, the sourcing. It's going to wait for everything to finish. Then it's going to run the simulation on the left side, and then it's going to run the simulation on the right side. Don't forget that these nodes, you need to double check if the base name and everything is set correctly for all of them. Just double check. Sometimes when you copy a node, the base name changes back. So if, for example, if I do like this, after I cook, this changes. Okay, it's just because I didn't cook, but yeah. So, okay, then you just need to come here and do generate node, save and continue. Because you choose the last one, it's going to generate all of the above. Why is the merge? I don't think we need the merge, sorry. We can do like that. Yeah, this is the correct way. We don't need the merge. Yeah. The merge is going to would combine both of them if you want to split. So yeah, this is the more appropriate way of that. So I need to generate this again. Generate, save and continue. Everything is 240, 239, and 239. Yeah, it's correct because it starts on the 1 and goes all the way to 240. Actually, should be 240. I'm not sure why, but it's fine. It's going to work. Let me just double check. Yeah, yeah, yeah. I don't know why. Yeah, now it's all correct. I don't know why it was giving. Probably there is a reasonable explanation. I don't think it's a bug, but I'm not sure. So if you dirt the node, it just cleans up. So now you just go and cook the node. I already did that. So see you in the next lesson. And yep, it might take a little bit, but I don't think for comparison the main simulation of the Whitewater should take longer than both of them. That's my opinion. So if it's taking too long, maybe you need to reduce even more the resolution for the Whitewater. Thank you. Bye bye. So I ran both of the simulations. I had like the caches before. So basically, this is the result. I have like in my simulation around 2 million points on the side simulation, and less than a million, I guess, for the top one. Yeah, 500,000. So it's very little. But if you look from the camera, let me go from the camera, and I change this to be able to see the size of the points. You see, it's pretty like filled. Like there's not a lot of holes, and it's going to hold pretty well in the render, I guess. So this is enough for the distance, and we only have 500,000 points. It's really good. Now, what I want to do, let me show you what happens. When the wind is really strong, the particles there on the surface, because of the surface tension of the water and other properties, it just stay like on the surface. But once they get a little bit out of the water, like the wind is going to blow them away in creating a very nice. You see, like this type of thing, like here, when you see because it's breaking, the wind is just going to take these little particles away and created this massive. Look the amount of white water here because the wave just broke. So once the particle just go a little bit away from the surface, it's just going to be blown by the wind, not necessarily because of the impact of the boat, but just because it's just breaking. So that's what we need to do. And for that, let me explain the stages that we're going to do. First, I want to create a wind field. The wind field just gives like some direction and some little turbulence, but it's not like a smoke simulation where the particles can go back and forth and do all kind of things. For now, we're going to just create a regular wind tunnel with some turbulence on it, following the direction more or less of the waves. From that, we're going to select the particles that we want, probably particles around these top areas, around where the waves are breaking, and we're going to advect them by this wind on that direction. And then we're going to run a smoke simulation based on this emission as well, so we just have like more interesting twirls and all that. So let's build first the wind. So I'm going to grab all that for now. I'm going to move this here, and then I'm going to create another one of these. Let's call this, doesn't need, we're not going to create a lot of those, so it's fine. Yeah. Copy and paste. Let's call this forces, and let's color it yellow. Let's place a geonode and call this wind. Let's dive inside. And now I want to get the bounds. So what I'm going to do, I'm going to get like the object merge, and let's merge the main scene because I don't want to have this effect on the back and the other ones because we can't see them properly. They're further away, and we just need for this foreground area. So what I'm going to do, I'm going to just grab our render geo because it's, yeah, this one, to save, copy here. Let's do like a time shift just to hold. What I'm looking for is just the bound of that, right? So it's just the bound. I'll get that in this frame, and I'm going to create like a bound. Yeah, I'm going to extend now the bound. So I want to, we don't need to go below. So this is the under part. 2, 2, 5. I want to get like a higher, and 2. Yeah. So that's our bound. If we look to the our surface, it's this one. The bound is here. So it's going above. We might even increase the bound a little bit on the top. Maybe we go like 6, just a little bit bigger. And then we're going to create a volume, right? So the wind, we need this to be a volume, so we can have like a the information inside, all inside this bound that we created. We're going to create a bound for that. So first we can do like a, let me just unplug this so it doesn't calculate because a big error. I would say by size, and we can make it very low res, 1 or even higher. All right. This should be a vector, and we can call this val. Can set everything as is, and then let's place like a volume velocity node. The volume velocity, it provides the power to add velocity values to the velocity, because here we set everything to 0. We could just set like some value for that, but for that to work, for that to visualize, we can place a grid here so we can see what we're doing, and we can, let me just do the grid like maybe 50 by 50. Yeah, we can keep like that because we need to scatter points. So let me just scatter. All right, good. Here's our points. The grid, I want to get like to, maybe if we do like if we convert this to VDB, let's do a VDB convert, because this is a regular Houdini volume. What we want to do is just convert this to VDB. So now it's is blue, and we also need to do a vector merge. It's called vector from scalar. So it combines these 3 floats into a vector. So if we go in here, now we have like a vector, and this we can do now like a volume trail. and the volume tray required some points and also some velocities. So for now, we don't have anything because we didn't set any constant velocity to that. So now you can see. Let's start making like 10. We keep 1 just to give a little lift, and 6. All right. So also I want to add like now we can see the velocities going. We can just maybe center like 2 just to visualize. Yeah, everything has a very direction and basically not much noise, so we can add some curl noise to it. And the scale of the curl, I want this to be like 3, so I want strong, but the size I want really large, like 8. So you see, if I make it like a 0.1, for example, every little one it changes direction. But if we make like this 20, you see like these big movements or of the swirl that particles go together. I think 8 or 10 is a good value. Yeah, that's it. We have our tunnel. You can see like if you change this by time, it allows to see it properly propagating. And if I disable the noise, everything was just very boring. And now you can see that. And if I make this 20, you can see the patterns. If I make like 0.2, you see how noisy it is and doesn't change nicely. So 8 is a good place that we have like a lot of cool variations on that. So now we can do like a no and say out wind force. This is the wind force that we need. So out wind force. And do like that. Awesome. So now we have our wind force. This is just a visualization, but the wind force is a vector field and it's very low res, but it's what we need. We don't need more than that. So in the next lesson, we're going to start building the particle simulation using this field to make the particles that emit from the crest of the waves to just fly with the wind. Okay, see you there.